Good morning. Since last time we looked into the precursors of cable-stayed bridges, roughly until World War II, we now start with the modern true cable-stayed bridges, and we distinguish these in steel cable-stayed bridges. Those were the first, then concrete, then composite, and finally we will deal with special systems of cable-stayed bridges, meaning series of cable-stayed bridges, if we have several, one behind another. We will look into bridges which are underslung or which have low stays above, and finally we will have a small look into cable-stayed pedestrian bridges. So that's our program for the next, I think, 5 lectures. As mentioned, we start with cable-stayed steel bridges. Simply, the reason is those were the first cable-stayed bridges. Initially, steel appeared the one and only material, not only for the beam, but also for the towers. That changed later on with more experience. So, after this little introduction, we go into the beginnings of modern steel cable-stayed bridges. The main change, which was very essential for the use of cable-stayed bridges, was the change in the general cross-section of steel bridges. Until, I just say, World War II, we had beams, we had cross-sections in which all parts acted separately. The main girder just acted as main girder, the cross girders acted separately, and then the roadway itself just distributed the wheel loads to the longitudinal girders. Now, with a modern orthotropic deck cross-section, all parts act together. We have the orthotropic deck, which acts as top flange of the main girder, as top flange of the cross girder in transverse direction, as the top flange of the stiffeners for the steel plate here. And in transverse direction, the orthotropic deck is the web for, from wind transversely, is the web for the top flange and bottom flange, which are the main girders for in the transverse direction. So everything works together, which is quite important in general for the good use of material, but also because we have moments and normal forces. And if you try then to fit those in here, you come very quickly, it doesn't work. So this is a very important thing. By the way, orthotropic deck, I presume you had it in steel structures. The name comes from orthotropic and orthotrope anisogonal. So it's rectangularly non-uniform stiffness. And it's an artificial word which has been built from the two, from orthogonal and anisotrope. Now, we had the publication from Dischinger in the late 40s stating use of stay cables for suspension bridges with good outline of the characteristics of these stay cables. And then immediately the first bridge after the war in this connection across the Rhine River at Duisburg-Homberg, 1954 completed, used for the last time a mixed system, some sort of a suspension bridge, but not a continuous suspension cable. The cable, like a stay cable, connected to the beam, self-anchored, so the normal force runs here. And for me, the obvious thing was its construction. Now, a self-anchored suspension bridge works only once the beam and the hangers are complete, otherwise you can't take the normal force. So, for construction, one used auxiliary stays to keep the beam in place. Now, I think that's very obvious. If you construct the bridge like this, then you should use these stays not only during construction, but also in the final stage. And that's what happened. People realized the mixed systems are a waste, so we go to completely stayed bridges. And the first one then was the Strömsund Bridge by the German contractor Demag in Sweden. And the main engineer was Dischinger, who advised on this bridge. The main characteristics have already been used for the Strömsund Bridge, completed in 1956. And then started what we generally consider the real beginning from which then cable-stayed bridges, in a way, mushroomed, went all over the world. And that was the 3 bridges across the Rhine River at Düsseldorf, the so-called Düsseldorf Bridge family. It was designed in the early 50s, all 3 bridges. This is a model picture from something like 1955 or so. It took 20 years to build the bridges, but they were built unchanged from their initial design. We have here the first one, the Düsseldorf North Bridge. We engineers tend to stick to the original name which was used during design and construction. That was Düsseldorf North. Modern days, then a politician comes in and it gets the name of a politician. So it is the Theodor Heuss Brücke. I generally stick to the old names which are, for example, in the publication and so, and in the book or script I sometimes give the other one in brackets. So for me this is still Düsseldorf North. Then the second build was the Kniebrücke, because of the bend of the Rhine. And the third one was Düsseldorf Oberkassel. Now, since this was the real start of the worldwide development, I would like briefly to point out the people responsible. First of all, Friedrich Thams, an architect who worked together with several of these at the Autobahnen in the 30s. And he was heading the city planning office, and he had deep understanding of cable-stayed, of bridges in general. And he said, okay, these 3 bridges, I want them light and visually attractive. So they should all have the cables in parallel, in harp arrangement. And then he said, for the suspension bridges, where we had the towers as frames with a cross on top because we have heavy wind from the main cables up there, I don't want that anymore. I want freestanding tower legs to indicate that we have here a different type of bridges from suspension bridges. And so these are the 2 visual characteristics which I say visually tie together these 3 Düsseldorf bridges, although each in itself is structurally quite different. 2 cable planes, 1 cable plane tied back here and so on, they are different. But visually, the harp arrangement of cables in parallel, and if we have 2 towers, here we have only 1, here and there is no cross girder on top. That in a way makes them the bridge family. So we had here Thams as the city architect, important, and we had Erwin Bayer as, say, the city engineer, and those two had the guts to go along with this new bridge type, which for civil servants is not the easiest thing. Civil servants tend to use what's proven, and not new ones, and they had the guts. Then the engineers for this design was Fritz Leonhard and his partner Wolfhard Andrä, which later became Leonhard and Andrä. Hans Grassel, an important from Austria engineer. His major design office is now, there are two run by his sons, one in Hamburg, one in Munich. And Louis Wintergerst, who went on his own later, not far from Stuttgart. I had the pleasure to know them all personally. These, of course, quite closely, but these as well. And they were important, interesting people. And now then, we do not want to forget what is the same, has the same importance. And those are the contractors who have to build these things we engineers think up. And there we had at that time an outstanding steel contractor, Hein Lehmann, probably in its sophisticated ways the best in the world. And Hein Lehmann built all the early cable-stayed bridges plus many others. And at that time, the detailed design and construction engineering was done by the contractor. Unique for Germany that German contractors had design offices. All over the world they had not. There always the consultants did the detailed design for the contractors. It's coming back now. Main contractors have less and less own design capacity, and they come back to the consultants to do it for them. But at that time, there were very few consultants. Leonhard, Homburg, Grassel, but that all started only, that was small. And so Hein Lehmann, there was Karl Lange, there was Mr. Weitz, of whom I only got a picture now, and then Volker Rademacher and Ramberger. I've known these two personally quite well. Outstanding engineers who produced also outstanding publications, and I quote from Volker Rademacher in the scripts quite a bit, especially from construction engineering. Okay, that was basically the Düsseldorf bridge family, the background. We have here first the Düsseldorf North Bridge. I'm just thinking, there's a wrong picture that's symmetric. I don't know how that happened. You see it there. It's symmetric, about 250 meters. Then we have the Knie Bridge, which with its, 324 meters, it's difficult to read here for me, was built by free cantilevering. The contractor didn't intend to, when he bid for the bridge, he wanted to place an auxiliary pier in the middle of the river. But then it turned out that with heavy ship traffic, to protect this auxiliary pier against ship collision would have been so expensive that he said, we can't do it, we do free cantilevering, which is unheard, 324 meters, which was unique. If you double the bridge, which would be the same structural effort, you come to 640 meters, which was only reached actually in 1995, I think, by Normandy, 30 years later. So that was an outstanding job these people did. And finally, Oberkassel, which had the speciality that you couldn't interrupt, that's a main inner city arteria, and you couldn't interrupt the traffic there for elongated time. So it was done that you build the new bridge parallel to the old. The old is still in use. Then you, over a weekend, you can take the traffic around over the new bridge, demolish the old, then shift the new bridge transversely into the position of the old. There was no way of deviating. It's all tight inner city traffic there. And then finally you have the new bridge in place of the old one. It's about 45 meters over here, and you can only do it by stressing the cable such that the support reactions become zero, and you can take it off and shift it then with hydraulic jacks 45 meters, something over here. 10,000 tons coming down here. It was the biggest bearing at that time. Quite a job. Okay, now the Rhine River is the major commercial traffic arteria in Europe. It connects the highly developed industrial countries, Switzerland, France, Holland, Germany, Belgium, with the North Sea and thereby with all the world. And it's very highly traveled. And so you cannot place a pier within the navigable range of the bridge. So you need at least 200, 250 meters up to, say, something 350 meters. Those are the largest spans required in Germany. It's something, but unfortunately we do not require longer spans in Germany. That's the Rhine River, and that it is. So 350 meters is a nice, but in world scale, it's small. So if we want to do considerably longer spans, we have to go abroad. The French, for example, are more fortunate. On one hand, the Seine River near Paris requires 850 meters, or the very deep Tarn Valley required things. We do not have the requirements in Germany, so the Rhine River bridges are the biggest we have, roughly speaking. I mean, Strelasund and so on. So there was no bridge standing after the Second World War across the Rhine River. They were all destroyed. They had all to be rebuilt, and the economic system of cable-stayed bridges came in handy. So a great number of them are cable-stayed bridges. In the book or in the script there is a plan and a listing of all these. I just show the next one special. We have the Severin Bridge in Cologne, which has the first A-tower independently supported on the piers, the beam running freely through it. And then came a big step with Bonn North Bridge. I think the official name now is Friedrich-Ebert-Brücke, but there are several Friedrich-Ebert-Brücke across the Rhine. So Bonn North, I think, is good enough for us. Bonn North by Helmut Homburg, another great bridge engineer in Germany after the war. He made the big step from individual groups of ropes combined to a major stay, with stays at long distances, say 50 meters, to very close support of stays, so we call them multi-stay bridges. So we came from bridges elastically supported at distinct points, say 50, 60 meter distance, to a uniformly elastically supported cable-stayed bridge. And here he had a distance at the beam of 4.5 meters. Very important advantages. First of all, you just can use simple single lock coil ropes, 100, 120, 150 millimeter diameter, but you can anchor them easily at the tower and at the beam, and you install units at the distance of the cable anchorages. 4.5 meter cable distance, So the pieces, the slices of the cross-section also have a length of 4.5 meters. You lift a section, install the cable, next one, go on, go on. You don't have to bridge long distances between stay cables. Easy construction. And because the concentrated stay cables consisted of several ropes, they were difficult to protect against corrosion. You cannot get to the inside, you know. There were all sorts of tricks, but with time they all corroded. So those are the main advantages. Simple stays, simple anchorage, simple construction. Big step, and that is from exceptions, if we take some exceptions into account, the type of stay cable bridges we use with multi-stays. This is Helmut Homburg, an outstanding engineer, mathematician. He made influence surfaces for slabs before computer age by differential equations and things like that, and was an outstanding man to calculate. In the scripts we have various examples from him. He was one of the first who could calculate cable-stayed bridges. Next interesting one is Mannheim-Ludwigshafen across the Rhine River. This is the first, what I call hybrid cable-stayed bridge. Hybrid, meaning we have different materials over the full length of the main span and the side span. Typically, we have a light steel beam as a main span, and we have a heavy concrete beam at the side span. So we can anchor the weight from the main span to the heavy weight of the concrete beam. Two materials. It has also been done, it's always concrete, or normally concrete in the side span, steel here, but you could also use composite, and so on. That is all the world record spans we will see later use hybrid cable-stayed bridges. I classify them here under steel bridges because the main span is steel, but the combination steel-concrete is important. Rheinbridge Speyer had a new idea by having the concentrated backstays here. This was possible, this was overland, so there were supports, same material, steel, but it is less expensive to support this beam directly by short piers than take it up to the tower and go back here. So concentrated backstays. Another new one, Neuwied, also by Homburg. Now in Neuwied, across the Rhine River, we have an island more or less in the middle of the Rhine. So it offers itself to build a tower here and stay left and right. But then we do not have these distinct backstays to keep the tower head in place. So we have to make the tower itself stiff by using an A. And so a load here goes up, runs up the cable and is split in tension and compression and goes down directly into the foundation. We have some more examples, and I think the examination last or the one before the last, I asked to calculate such a system with the forces in the tower legs. But we had prepared it in the repetitorium before. Another important hybrid bridge, Flehe, a little bit longer than before. Steel beam here, concrete, I think 700 meter long concrete approach bridge. And again, the steel beam here is anchored in the heavy concrete beam. I was project engineer in 1974 for this part of the bridge, so I know it quite well. Another special one, Ilvrich Bridge, also near Düsseldorf across the Rhine River. It's close to the Düsseldorf airport, meaning the height of the towers was restricted due to the planes landing and leaving the airport. So instead of having the cables up like this and a vertical tower, since this height was only permitted and the cables need a certain minimum angle to have them economic, the tower was split in a longitudinal V and here connected. So we have basically the same forces in the stays, and here we just tie them together. One of the latest, or the latest, Rhine River bridge is Wesel. Please be aware the truss in the background belongs to the old bridge that will be demolished. It looks a little strange, but it's not. The beam is very slender and the truss behind will go. It's some similar as Flehe, only we have here, well, for the second time, parallel strand cables instead of the ropes, new for Germany. Now some more. We had the Düsseldorf Bridge family. We had important Rhine River bridges. Now we go to some also special steel cable stayed bridges, and then come to the record spans. Ludwigshafen across the railway, a four-legged tower. Bratislava in Slovakia, the only one until now in the world which has a restaurant up top, which, you know, we have it on all TV towers, and why not? It's a nice idea, but it has never been repeated, but it's there. The first cable-stayed bridge, major cable-stayed bridge for full railway loading in Argentina. Two identical bridges, actually, that's near Buenos Aires, between the cities of Zárate and Brazo Largo, 330 meters, one-sided for heavy ore, Cooper 80. Railway makes it quite unsymmetric transversely. An important bridge with many new ideas. For the first time, the braking forces from the railway, which are important, are distributed on both towers, which is always a little problem, by using hydraulic jacks between the beam and the towers in longitudinal direction. Now, these hydraulic jacks, for temperature, very slow, they do not react, and so the beam can elongate or shorten between the towers without bending the towers outwards or inwards. However, if we have a rapid load, say braking of a train, then they act like rigid connections and distribute the braking forces equally over both towers. The trick. It's a theoretically beautiful solution, especially here. We are on up to 80-meter high piles, very bad soils conditions. And so you can imagine the braking forces 50 meters up on these piles cause major moments. The only shortcoming is you have to inspect them regularly. I mean, they have these inner workings, and I'm not so sure in some places in the world that that's always so properly done as it is supposed to be done in Germany. That's why I would be hesitating to do it, but it seems to work. And it was the only way to make it stand up. Colleague of mine, Rainer Soll, was in charge. He went there, I think, 1969 and stayed there for 4 years, doing detailed design, construction engineering supervision on site of these important bridges. Well, at the same time he worked in South America, and I started work in the US So we worked there in parallel. An interesting bridge by the famous engineer and architect Santiago Calatrava. Quite unusual. We have a cable-stayed bridge here with an inclined tower, but no backstay. Unique. Now that means for permanent load, the system is balanced. The vertical forces here balance the weight of the steel beam. But of course, for life load in the main span, it has to act in bending, which is not the flow of forces we consider appropriate for cable-stayed bridges. But it is a sculpture. And Calatrava claims he had developed this form from the flight of a bird there in Spain, and the cross-section from a bull's head, which plays an important role in Spain. Well, that's what is said was behind it. And this is Santiago Calatrava, an outstanding engineer and architect who builds beautiful sculptures, not only cable-stayed. You may have seen done railway stations, he has done arch bridges. The flow of forces, as I say, I'm not so artistic as he is not always correct, so I wouldn't do it, but it's an aesthetic statement he does. One of the latest in Germany, outside the Rhine River, Strelasund, you may have gone to the island of Rügen, where you have seen it. We will have a special lecture as an example for cable-stayed steel bridges at the end of next semester. And just 6 weeks ago completed, Sava Bridge, Ada Ciganlia, across the Sava in Serbian and Save, we say in German. And this is a harbor, and this is steel, and this is concrete, but unique insofar as the concrete side span is not supported by piers, but is balanced with the steel, and we still have then backstay cables. It's a very delicate situation. It took us some time to find out how to do it, but we won in a competitive design, contractors poor. So it is the most economic solution, but not as for the hybrid bridges we've mentioned before, that the concrete bridge is heavy and rests on piers and you can tie down. No, the concrete part is also suspended by the stay cable. So it's a rather delicate balance there. You have to make the weight of the concrete just right, that this part, shorter part, balances this long steel part. But we succeeded and was selected and was closed about a month ago. Now, finally, record spans. We have mentioned these early ones. It started in the 50s, Strömsund, Düsseldorf, Severin, Knie. Then we came up to something 350 meters, Neuenkamp. And then we go like a straight line, but to the current 1088 Sutong. But don't extrapolate this line now into infinity. We don't know how it goes on. Probably it will slacken off a little bit. But since here, say, Saint-Nazaire and so on, it's a straight line. Okay. Saint-Nazaire took the record 404 meters in 1975. That's across the mouth of the Loire River in France. And then it took about the record held for about 20 years, which is quite unusual. Until then, we nearly doubled it. My friend Michel Velogeux, an outstanding, you can mention him here, an outstanding, maybe together with Jacques Combeau, some others, active, outstanding French bridge engineer. Then he jumped from 404 to 856. That's also unique, that a new record doubles, more than doubles the one before. It's a hybrid bridge, steel cross-section, concrete side span, built by incremental launching. This part, the concrete, goes about 120 meters into the main span by free cantilevering, and this then also by free cantilevering. We will have a special lecture on this also at the end of the next semester. An outstanding bridge. Then, a few years later, and not very much longer, the Japanese conquered the record span. Initially, they had planned to do a suspension bridge there, but found that due to the bad soils condition, the abutments to which the main cables would be anchored would have needed to be very large, very big, very heavy, too expensive. So they changed to cable-stayed with a partly hybrid. They have here the outer part of the side span is in concrete as a counterweight to the main span. Then came Stonecutter. During the design phase, it had the world record with 1,018 meters. We will see later for under the heading construction of the Stonecutter bridge. But as it happened, Ian Firth, a friend of mine, was the guiding spirit behind the original design. And then the Chinese with the Stonecutter in Hong Kong is also Chinese, of course, but it had still the special status. And in, say, mainland China, Sutong Bridge, they started later, but finished earlier. So with their 1,088 meters, the Stonecutter Bridge never formally held the world record, but I thought I'll put them in here this way. I had the same. When I did Pesco Kennewick, during the design in the US, we'll see it later, it had the world record. And then the French started later with the Breton and were faster, 20 meter more. So we never had the world record. These things happen. Okay, I think that was, in brief, the development of modern steel cable-stayed bridges, starting in the 50s, the main point being the Düsseldorf bridge family, the Rhine River bridges, and then all over the world. And now we are with 1,088 meters, the longest span in the world, the steel cable-stayed bridge. Thank you.